while carrying out both research projects at the nearby observatory of the Brera Merate. And today he will talk about X-ray quasi-periodic eruptions from the nuclei of low-mass galaxies. The floor is yours.
Thanks so much. Can you hear me well with the mic? Hi, thanks for this. I've been a neighbor here for a few months now, but I joined in January, so everything is pretty much already starting in both in MIT and CFA. So I'm happy actually to present my work here. One thing I should mention is that I'll be here, I think, most of the week. Today, and Wednesday and Thursday too, in a guest office somewhere. So you can just let me know via email or just fill the Google sheet if you want to meet. I'm going to present these transients today, but I also work on general massive black holes in low-mass galaxies, and I know that some people here do that observationally or theoretically, so in case you want to have a chat about that too, let me know. The talk today is going to be focused on QPEs, these fairly new type of transients that were discovered a few years ago. I'm going to guide you through the basics in the observations and a little bit on the models that have been proposed. And I don't know what's common, but you can stop me during the talk if you want to ask a question. I don't mind actually. Right. So I shouldn't explain this here, the CFA, the energy group, but like usually, when you look at a galaxy, if it's active, you see a point-like source. If you care about what's coming from the nucleus, it's usually bright enough that you don't need to worry about other contaminant factors for most of the galaxies. And since the birth of X-ray astronomy, we always knew that these galactic nuclei vary really, really fast. In fact, they varied so fast that if you, in terms of compactness of luminosity over a radius, nothing else apart from a black hole that we know of would have such a compactness. So it was among the first pieces of evidence, indirect perhaps, of the existence of black holes in the central parts of the galaxies. And for a few decades, we were expecting more or less extreme variability from these nuclei, but in somewhat of a stochastic fashion. And then a few years ago, this changed when Giovanni Minuti and collaborators were looking at this galaxy in the X-rays, and it's a fairly small galaxy. It was doing somewhat interesting things, but it was mainly being observed because with respect to Rosat in the 90s, when there was just an upper limit, and it could have been just another low-mass galaxy in which you don't even know whether there's a black hole in it in the first place, or it's probably just quiescent. And then in 2010, experiments Liu found the X-ray flux to be brighter more than a factor of 100. And for the following decade, this group and other groups have been following this source up because it was showing like a mild decline. And together with other properties, it was worth having a look at it, but like not particularly so for the variability, because in fact, it was quite boring. I've shown you this plots, from the 70s or 80s or whatever. This source was strikingly boring in terms of variability for being a galactic nucleus. And then at the end of 2018, basically this sort of behavior started being seen. This is an observation from December 2018. Then obviously, when you realize you haven't broken XMM Newton, you go for it again, and then you actually realize that these bursts recur every 9 hours or so. So it's a behavior that was never seen before from the nuclei of galaxies, and it required a new name. And someone chose this name to be quasi-periodic eruptions. And now we have a few discovered, and I guess we have to stick with this name for another while at least. And basically, immediately after the discovery of the first one in 2018, the same group went through the archives and found that this other low-mass galaxy showed this single burst in the year 2000 in the archives of XMM Newton. And then they followed it up again, and then they saw a few more bursts. So effectively, within the next few months already, this group found 2 of these sources. Then work led by a student that is now actually a PhD student at MIT, working with Riccardo and myself. Back then, I think he was a summer student, and he was applying his periodic search algorithm through the archives and found this other candidate, which still is a candidate today, just because effectively it showed a flare and a half and nothing again when it was looked at it again. They looked at the source again in 2021. So effectively, based on serendipity and archival searches, 2 sources and a half is what people found until a couple of years ago. And then basically That's pretty much the state of the field when I found myself in it in a way. I was back then a PhD student in Munich, and I actually I asked myself, where was I in December 2018? Because I guess it's a long time ago, but in terms of PhDs and postdocs, it's fairly short time. And I had to go through the pictures in my phone because I actually didn't particularly remember what I was doing. I think the closest in time to this observation was my mom's cannelloni for Christmas. So I was completely unbothered and unaware about these sort of things back then, and having a good time in a way. And then, you know, I think you have to be at the right place at the right time as well, because when the first discovery was being presented, it was, I think, for the first time ever at this conference in Bologna, which I think some of you might even have attended. It was a big one in Bologna in 2019. There's hundreds of people here, and I was right there in the back, you know, again, probably just, I wanted to get to the lunch before all the others, and I was in the back trying to sneak out and get my food. But then eventually, when this discovered was presented, you know, I realized I was MP and Rosita was just launched. So I discussed with my supervisor what we could do to find more, and eventually we figured out that we could. Just a little, maybe slide or two on Rosita. I know this is potentially an X-ray audience, but not necessarily. So basically, the key that I'm going to come back to is that QPs can only be discovered through X-rays. And Rosita is this X-ray telescope that MPE and the Russian Space Agency launched in summer 2019. It's an imager. It's if you're familiar with X-ray telescopes, it's more kind of like X-ray telescope similar to XMM Newton rather than Chandra. So collecting area in favor of angular resolution. And this is a plot that shows that it's basically, for the X-ray astronomers, this is the effective area. For others, is basically how good your telescope is in getting a number of photons in a given amount of time as a function of energy. And just to show that Rosita in red is right at the top in this. And on the right, you can see the field of view compared to XMMs and Chandra. So it's great for performing survey, which was actually the point. And in fact, Rosita was sent to L2. And the idea was that it would have scanned the whole sky by basically rotating the field of view in the ecliptic plane from north to south, and then completing the whole revolution together with Earth, and then performing a full sky survey in 6 months. And before, operations were interrupted a year and a half ago due to the war in Ukraine, and they haven't resumed since. But at that time, 4.5 full sky surveys were taken. So this is still a huge amount of data to go through. And just as a brief comment, the German half of the sky will be actually released at the end of this year. It's just a matter of when the catalog paper, the release paper is accepted now. And the point that is relevant for this talk is that this is not just an image, a single image with a single exposure at every place, but it's rather a stop motion animation, in the sense that the field of view scans overlap partially. So the same, a given source is observed for a few times before it's not observed again for 6 months. And basically the pattern is the following. So there is an exposure of 40 seconds every 4 hours. So 40 seconds is the time that the field of view spends on the source. Then 4 hours is the time that the field of view spends to revolve around the ecliptic plane and go back to the same point. So the idea was, imagine we have a source like this, you know, emitting QPEs. What we could do with Rosita is basically use our sampling, which is fixed on the full sky, hoping to find something like this, a galaxy that would pop up and out from our, you know, observations in a significant way, obviously. But then eventually, if you think about that, Rosita only sees something like this. This is obviously just a candidate for repeating variability. But if you think about it, we don't really know anything that, you know, produces something like this in galaxies apart from QPs. And then it kind of was a fair assumption, because that's exactly what happens. So whenever you see something significant from a galaxy that flares repeatedly in X-rays, so far it's always been a QP or something anyway interesting. And that's what we did. That's what we applied to the Rosita archives. And now you see on the top quantitatively, you know, the light curve that I basically cartoonized before. And the alert from Rosita is in red, that comes from basically on top of these two galaxies, and follow-up XMM Newton observation pinpointed it to the nucleus of these two galaxies. This was the result of the first year of operation, data mining, and then in the second year of data, sorry, before going through that, This is what you get with a follow-up observation, which it's what I mentioned. From here you get, from here you get candidates, and then you confirm it. You can confirm it with other X-ray telescopes. So Rosita that wouldn't stop its survey. You need another X-ray telescope to confirm the nature of these candidates. Just to show you that this source required, an 11-day data set to find a batch burst with a periodicity of about a day, and this other source basically required a day of data to collect a few bursts and a periodicity of a factor 10 less or so. And it would look pretty similar in our data stream. So we are biased, of course, given our sampling, but we can span 10, like a factor of 10 in timescales, which is pretty good. Then during the second year, we found two more that I'm about to submit this paper, hopefully by next month. One that recurred every 20 hours or so, and another one with somewhat of a scattering arrival time, but recurring every 10 or 15 hours. And their properties are pretty similar to the other two Rosita QPs. One thing that I want to mention now is that, if you do like a fast forward from 4 or 5 years ago when the first one was discovered, it's still a fairly slow pace because we have, 6 known QPE, secure QPE sources at the moment, of which 4 are public. So if you think about it, we definitely need to figure out how to use future X-ray probes to find more. Now, okay, we have a sample of 6. Let's do a little bit of sample statistics as much as we can. The basic observational properties are that these are fairly small galaxies of about 10 to the 9 in stellar mass, and estimates from optical lines point towards black hole masses of about 10 to the 5 to 10 to the 6. So small black holes is small galaxies. So definitely not your usual galaxy and usual AGN in any way. This is where they would lie in a black hole versus stellar mass relation, where basically there are many data points, and if you are ambitious, you can see that basically we are about here now, and maybe with more sensitive instrument, we can actually find intermediate mass black holes in the center of low mass galaxies, which is pretty cool. Regarding the X-ray properties, the spectra, so that these sources are normally detected even when they're not flaring. So the quiescent spectrum is what you see here in red. It looks like basically like the exponential decay of a thermal distribution of a thermal spectrum. And if you know what to expect from a galactic nucleus with a black hole of about this mass is, well, usually a power law that you would expect from any AGN, but also you could see the VN tail of the SED of the accretion disk for these low masses in the soft X-rays. We don't see anything above 1 kV or so in quiescence. So there doesn't seem to be a corona, standard X-ray corona, or maybe it's just too faint to detect it. But we do see these exponential tails. So similarly to X-ray TDs, we basically see the ISCO of the accretion flow in the soft X-rays. And with respect to, if we compare now the quiescence in red to the peak in blue of these bursts, there still aren't like a non-thermal spectrum. Like even at the peak, it looks like, again, the exponential decay of a thermal spectrum. So it's nothing like the flares of Sagittarius star in terms of spectral shape that are pretty hard, and they extend to hundreds of kV and all that. So it's something that was never seen before, even in terms of spectra. Now, if you think about luminosities, this is also unique. Sagittarius star is the same mass, 10 to the 6, but flares at luminosity of about, 6, 7 orders of magnitude fainter than that. So clearly, we're not talking about the same type of events here. The quiescence is detected at about this luminosity level, and the flares are about 100 times higher in flux and luminosity. And if you think about the fact that these are 10 to the 5 to the 6 black holes, this is not too far from 10% in some plus minus, whatever you want to do with it. But it's basically something that makes sense if you know that these are fairly small black holes. Regarding the variability, we have that the average separation in between the bursts of the sources spans, a couple of hours to almost a day across these 6 sources, and their duration is also half an hour to a few hours, right? And usually, the time that takes to accrete material, even for these low masses, is 100,000 times, hundreds of thousand times larger than this. So this is not accretion related, most likely. So you have to think about something else. Now, why the quasi in the name? Because maybe from the plot by eye you can't really see, but effectively there is a large scattering, like half or most of the sources in arrival times, and some of them are really, honestly, you get to the point at which if you told me this is not periodic, I would actually agree with you. But we're getting to the point in which we're trying to model this anyway. And there are reasons to think that the sources that are more regular in arrival times and more complicated could still be modeled with the same prescription. I'm gonna say that in a second. Regarding the lifetime of these sources, so all the ones that have been discovered are still emitting bursts, so it's at least a few hours. And there is, in this particular case, evidence that bursts have been ongoing for a couple of decades at least, so few years to a few decades. It's something ridiculously small for a galactic nucleus, but for us, it's pretty convenient. We can actually spend some time designing strategies to study these sources that don't just disappear. Regarding multi-wavelength properties, we know that they don't show any signature typical of AGN, so no broad lines in the optical spectra, no photometry in the infrared indicating the presence of a torus. This is a compilation of the spectra around the H beta, and some of them show narrow lines, some of them don't. It doesn't really matter too much anyway, because if you have narrow lines, these are timescales, I don't know, 10,000 or 100,000 years ago, representative of the sort of timescales, while the X-rays are telling you what's happening now. Regarding variability in other wavelengths, we have found none so far in the V, in the optical, in the radio, with the caveat that low mass galaxies, in low mass galaxies, the galaxy actually dominates most of the SD potentially, unless you get HST or GWST level photometry, which we haven't gotten so far. So it's still TBD, but surely there's nothing like this in any other part of the SED, only in X-rays. Now, I have just a few minutes now left. I'm going to guide you through, I think, the leading interpretation at the moment, although I'll just convince you that it's actually not unique. But what people are focusing at the moment is on a high mass ratio binary in which there is the central black hole of about 10 to the 6 and an orbiter, which is much smaller. It could be a star or a black hole of a few tens of solar masses. And from a theoretical point of view, this came in a couple of flavors. So it's either like a star or a white dwarf undergoing partial tidal disruption at pericenter. This is, in my opinion, I think the least favored of the models. In particular, we know that there is an accretion flow here, and I think the only paper that tried to model it in this framework of partial disruption is this paper of Wenbin Liu and Elliot Quetert, in which QPs are caused by the shocks in between the spheric material and the ambient disk. So this is one of the interpretations. Otherwise, people have suggested that collisions between the orbiter and the disk would power shocks. And this also makes sense if you think about the temperature and the spectra of these QPs. And I think these papers came out in the last couple of months, and they're the ones that have probably made a bigger effort in modeling a bit qualitative. It's still qualitatively, but all the observables. In this particular framework, a suggestion that it's quite intriguing is that this disk has to be compact for theoretical reasons. Otherwise, I think the orbiter will migrate on the plane and wouldn't do the bursts. And this is consistent for several reasons from the theory and observations, that this accretion flow is fairly recent and comes from a TD, from a tidal disruption. So this makes sense because these in spirals last something like 10 to the 5, 10 to the 6 years, and in these sort of galaxies, you have 1 or 10 TDs in the same amount of time. So it makes sense that at some point a TD happens, and it just reveals that there was this orbiter already in place there. So it also makes sense because in these galaxies seems to be the right ones for these interactions. For a couple of sources, we've seen that there is a nuclear star cluster, and for another couple, they seem to have happened in post-starburst galaxies. So galaxies that are not undergoing star formation now, but had a burst, I don't know, a giga-year ago or something. And from the dynamical point of view, which for me kind of like magic, but like everybody keeps telling me that these are the right galaxies in which these encounters are way more probable than in other galaxies. So in terms of both these extreme acceleration spirals and TDs. So this seems to be the right galaxy anyway. I want to draw caution on the fact that really, these are early days, and most of these comparisons have been qualitative. So now we're moving on to making quantitative tests of these orbital models. But alternative models that exist and have been proposed, for example, disk instabilities and the tearing of the accretion flow. With the last minute, I think I want to point to you perhaps just a teaser on whether this scenario is true. These sources, if this is the right model, which is still a big if, but it's getting more reasonable with time, would emit gravitational waves. So this would be the so-called MRIs that will be seen by LISA. LISA will only see black hole MRIs, so I'm not necessarily claiming that the same system will be detectable in both ways. But at the very least, computing the rate of QPs, if QPs are MRI, provides the first ever lower limit to the MRI rate, which nobody has computed so far from observation, only from theory. I'll guide you through this plot real quick. It's basically like number density of QPs as a function of X-ray luminosity. This is the quantity in megaparsec cube. And if you just assume like a given density of galaxies in a mass range, you obtain that, about this number of 10 to the minus 4. So basically that there is one galaxy every 10 to the 4 of about this mass that is emitting QPs at any time. So this is a number I can give you observationally. How exactly it relates to whatever they are theoretically remains to be seen. But if QPs are MRI, some number like this one, if you assume a lifetime, will be the first ever lower limit to MRIs given observationally. And I think I ran out of time, so I'll just guide you through my summary real quick. QPs are a new phenomenon in terms of X-ray activity, peculiar X-ray activity from galactic nuclei, but they're much more than that because they happen in a regime of black hole galaxy coevolution, which is poorly studied. So then they might be used as a byproduct for understanding how low mass galaxies might be activated, one of the channels through which they might be activated. We know 6 of them, 4 of which were found with Rosita with the project I led. A couple of candidates are still in the process to be checked, but effectively, Rosita has stopped observing, so we need to worry about, future X-ray probes, what they could do to study QPs. And just as a reminder, this is a scenario under current investigation, not necessarily the model, but people are focusing on I-mass ratio binaries. This has potentially huge implication for multi-messenger astronomies, but I want to draw caution that we are now in the process of testing this quantitatively, so it doesn't have to be the case yet. And with this, I want to thank you, and I'm happy to take your questions.
Questions?
Thank you, Riccardo, for talk. I was not clear on your 2 scenarios for the high-mass binary. So did I understand correctly that in the second scenario, the bursts will be caused by shocks as the small object crosses a previously existing accretion flow, and is this accretion flow from a tidal dispersion event which is independent from the orbiter?
It doesn't have to be. So this is just so from the modeling point of view, I think this is mostly required by the fact that an MRI wouldn't survive too many collisions if it's a star. It would be either ablated or it would just go on the plane. So from the evolution point of view, it cannot be really an extended AGN disk with the Brooklyn region of the torus and this gas density that goes down to thousands over G. Otherwise, the object would be in the plane and it would probably not even be seen observationally in any way. Also, from the rates point of view, if a star or a black hole gets in an orbit dominated by gravitational wave emission, once it happens statistically, that's very slow. It's an spiral that lasts 10 to the 5, 10 to the 6 years. In these sort of galaxies, theory and observation tells you that there is a TD every 10 to the 4, 10 to the 5 years. So statistically, since also this is not like a linear evolution, during this, if there is an embryo on an hour orbit, the probability of having a TD is, fraction of unity, or anyway decent. So it's not a far-fetched scenario theoretically. Observationally, real quick, we have seen QPs in sources that have shown X-ray decays prior to the discovery of QPs, and there is evidence of an anomalous carbon to nitrogen ratio in these accretion flows. Most of the sources don't have evidence of previous AGN activity. The X-ray spectrum is soft, like in TDs, and a source, which is a candidate yet, has shown half of a flare serendipitously in the archival observation of XMM after an optical TD. Now we're getting more X-ray data to see whether this is a QP. If this were to be the case, this would be the first unambiguous connection between QPs and previous TDs. And in this case, if that were to be true, you can also interpret the soft evidence in all the other cases in a similar way. So that basically there's just a TD, throws gas on an MRI, and then you see the interactions later on. It is far-fetched, but these are rare objects, and
yeah, okay. I'll have to follow up, but I'll ask you later.
Yeah.
Thanks.
I'm finding it really strange that we don't see optical counterparts of the AGN in the spectra. So, I mean, narrow lines, but I would expect seeing at least H alpha. Well, H beta is always higher because it's weaker, but in H alpha, you should be able to see something because if you don't, then this should put some constraints on the model of the stuff that you're dealing with. Because if there's no broadline region, like not that it's like obscured by the dust storage, but if there's just none, then this might be like a completely different angle that we should look at what we call an AGM, because this wouldn't fit the defined model.
Yeah, so basically we have no evidence of transients of persistent H alpha either. And in some cases, we have more than one spectrum at different epochs. It just never seemed to have been seen. Now, in these sort of low mass galaxies, I think you know more than me, sometimes it's trickier to see broad H alpha, even if the gas is there. So I wouldn't know. At the very least, it puts some sort of an upper limit on the density or whatever density profile or steepness you wanna do. If it is, you know, a newborn accretion flow due to TDs don't show necessarily broad lines, you know, especially the X-ray TDs. The optical ones mostly do. You know, there's this dichotomy that I guess it's poorly understood anyway. If these are the same sort of galaxy from a given orientation, similarly to X-ray TDs, then the problem might be the same that you have in X-ray TDs. It's some sort of low density combined to a galaxy kind of dominating the spectrum, unless you take HST spectra, which they don't give you easily. So yeah, I wouldn't say there definitely is no broadline region, but surely not an obvious case.
Okay, so okay. So if you have further questions, please feel free to fill the Google Sheet. I'm sure Riccardo has still a lot of space, so you don't have to fight for him. And now let's move on. Well, first of all, let's thank our speaker again. Let's move on. We have Kishalay there, another Einstein fellow at MIT, uses synoptic time domain survey in the optical and infrared band to study eruptive phases in the lives of binary stars and their effect on producing the diversity of stellar population and remnants. He helped build the first synoptic ground-based infrared time domain survey called Palomar Gattini. Okay.
Kittens.
Kittens.
Yes, yes.
In Italian is kittens.
Yes.
For his PhD thesis, and he's currently leading a large project characterizing mid-infrared transients from neowise space mission. And today's talk will be about the discovery of a planetary engulfment event in the galactic disk. The floor is yours.
Perfect. Thank you. Am I audible? All right. So thank you for having me here. I was honestly a bit confused when I was asked to give this seminar because I will be talking about high energy phenomena, but seen with low energy photons. So there's not going to be any mention of a single X-ray photon in this talk, just to put it out there. But so I will try to be very patient, and as I explain how we discover things in the optical and infrared for all the X-ray astronomers in the audience. This talk is going to be about this result that was published earlier this year. It was really made possible by a huge team of people who helped me understand a lot of the things that we are trying to understand. It was really unique in many ways. All right, so many of you would have seen this was on the cover of Nature this year, and I think it really caught the attention of many people because it's such an imaginative phenomenon and has something to do with the future of the solar system as well. And these are some of the more curious news headlines that were out there earlier this year. And honestly, I had to deal with a lot of emails from various kinds of people trying to explain how this is not a planetary engulfment and all kinds of theories. So I'm glad I'm done with that. But it was a very fun episode to interact with normal people, to talk about how we find things and how sometimes discoveries like these, which are really accidents, can really change our view of how the universe works out there. All right. So yes, this is of course from 4 months ago, but my talk is going to start with something that is 400 years ago. And that's because it's very closely related to at least what I was looking for. So I'm a time domain astronomer. We look for things that are going boom in the sky. And when you look at our history of things that go boom in the sky, it happens that the first recorded eruption of a nova. So novae are some of the best known eruptions. They're studied very well. They are very bright. And if you look at what is the oldest recorded nova eruption in Western history, you see this red dot over there. That's the oldest known eruption of a nova in Western history. This is this source that is called CK Vul, which was for a long time considered to be the oldest nova known in Western history. But what I want to convince you is that some things that we've considered novae are sometimes misclassified in the sense that there could be other exotic things. And this is definitely true for this case, because if you go and look at what this source looks like right now, this is what it looks like. So this is a composite image, of a multi-wavelength image, where you see in H alpha, there is this beautiful bipolar nebula that's coming out. There is this central dust enshrouded remnant that we see in the millimeter bands. And you see there is this bipolar lobe that is emitting in molecules. It's a millimeter wave emission. So the reason why this is relevant to this talk is that what today appears to be the understanding is that the first known eruption of a nova in the Milky Way wasn't actually even a nova. It was actually what we think this member of this class of things that we call red novae. So what are red novae? So red novae are these class of eruptions that, well, they look like novae, but they're red in the sense that this is an eruption of one of the best studied red novae in the Milky Way, which is called V838 Mon. What you see is that there is this cloud of gas that is reflecting light from the central eruption. And what I really wanted to focus on is that how this source becomes extremely red with time. And that's what this spectral evolution was also showing you. These are spectra of the same event taken a few months apart. It starts off at this relatively blue source, which a lot of blue and ultraviolet emission. But very soon, in a few months, the optical emission completely disappears. And all that remains is this red infrared emission. That's why they're called red novae. So red novae have been, well, in modern astronomy, they've been known for almost 30 years now. We can find these things. This is probably the best known one. This happened about 20 years ago in our own galaxy. And the characteristic features are that they start off as these bright optical transients, but they quickly transition into these infrared transients. They have these cold photospheres that almost look like M stars. For those of you who've seen stellar spectra, this is basically what an M star looks like, a very cold star. And the remnant itself, the reason it becomes so infrared dominated is because it gets enshrouded in dust. So what we know about these things, what we think these come from was really spearheaded by this one particular event, again, a red nova, where what you see here is that the light curves from the Ogle survey showed us that what you have here is two stars that were in a binary. They're slowly spiraling into each other. And as the spiral gets towards the end, the thing becomes dominated by tides, and you get a merger of the two stars that produces this bright outburst. And we know red novae, well, the interpretation is that red novae come from stellar mergers because we've seen at least one event in the Milky Way where we directly see the two stars merge into one star. And we have a few of these, about 5 of these known in the Milky Way. So, of course, now, since red novae were first discovered, we can now actually even find them in other galaxies. These are these things that we call luminous red novae. So luminous red novae are just the more luminous analogs of stellar mergers that we can find in other galaxies. And if you just ask, what do we know about the landscape of these red novae today? You can just plot the luminosity of these events as a function of the time scale over which they evolve. And this is where all of these guys lie. So these very luminous events, they reach luminosities of about 10 to the 41 in the optical bands. And the really low luminosity ones, they're around 10 to the 38, 10 to the 37 ergs per second. So these are the so-called luminous red novae. And what we understand today is that the light curves of these things, the emission that we see in the optical bands, these are powered by recombination of hydrogen. It's very much like a type 2p supernova, if you've heard of the type 2p supernovae. And if you take that model, then what you can show is that on this plot, you can create these contours of essentially the luminosity, and the time scale of the event gives you some estimate of the amount of mass that is ejected in these eruptions. So for the lowest mass events that we know of, or previously knew of, they ejected about a fraction of a solar mass. So these are low mass binaries. The most massive events, the luminous ones, these are very massive events. They eject sometimes tens of solar masses of material. These are coming from the really massive stars that are in binaries. So of course, as you can see, when you look at this plot, there is this gap of events over here, which are the events that are ejecting very low amounts of mass, something like 10 to the Jupiter mass event. So we can find these luminous events that in extragalactic systems, but what we were interested in was finding these low luminosity events that eject very small amounts of material. And these would be kind of the events where you have very low mass companions, things like that are not stellar massive companions, but more like planetary mass companions. So of course, if you want to look for these events, we're really living in the golden era for time domain surveys. I'm sure some of you would have heard of some of these optical infrared surveys today. Many of these data streams are completely public, so you can go and write your own filters to look for these things. And so so if you want to look for these events, it's really a nice time to look for these things. You can look for these eruptions in time domain surveys. And that's what the story is going to be about, which is I actually started looking for stellar mergers, just normal stellar mergers in these survey data. And one fine day, I came across this one particularly inconspicuous star. It's an archival image from about 15 years ago of this star that is, not special for any reason. It's just an obscure red star in the plane of the Milky Way. But then it did something quite spectacular. So this is an event that was detected in the Zwicky Transient Facility survey that runs out of Palomar Observatory. What you see here is the light curve that shows how bright the star is as a function of time. It was basically nothing. It wasn't doing anything. And suddenly in May of 2020, it underwent this outburst that it brightened to about a factor of a few hundreds over the course of a week, and then it slowly faded away. Of course, there are many things doing this in the galactic plane. It's very difficult to tell these apart from, other types of, white dwarfs and black holes and all of these things that go into eruption. But there was something special about this event that caught my attention at that time, which is that when I went back and took some follow-up observation of this source, it happened to be a very bright infrared source that was sticking around. The optical emission fades away, in a few weeks, but the infrared source was hanging around there for a year after the outburst. And you can confirm that if you just go and look back into the data from the NEOWISE archive. This is what the infrared light curve did. It also underwent this outburst. The infrared outburst, in fact, started well before the optical outburst. It undergoes a peak, and then it very slowly fades away. The infrared emission is detectable even today in WISE. That's how bright this is. Now, hopefully, this long-lived infrared emission kind of reminds you of this red nova phenomenon that I was telling you about, which is that they start off as these optical eruptions, but the infrared emission stays on for a very, very long time. And that's what we think we were seeing over here. So, of course, I won't go into the details of this, but this entire evolution from optical to infrared bands, we can show it by modeling the SCDs of this source. It starts off at this relatively bright optical source at early times. And then a year after the outburst, what you only see is the infrared emission that's sticking around. The optical becomes completely obscured. We can model all of this together to say that there was, that to explain the obscuration of the source, we need about 10 to the minus 6 solar masses of dust that was produced in this event. Spectroscopically, fortunately, we got some spectra of this source. This is a spectrum of the source during the outburst. Again, what you see here is that it kind of looks exactly like an M star. So red novae look like M stars. This is what you see over here. You see these titanium oxide and vanadium oxide bandheads. And if you ask what does it look like in the landscape of transients, you can see that this source looks identical to what we see in other red novae. This is the galactic red nova. This is an extragalactic red nova. They all turn into these M stars during the outburst. And that's important because that immediately rules out all of these other hypotheses like novae and extra binaries, which are all surrounded by hot gas. We see emission lines. This one source shows no evidence of any emission lines in its spectrum, just cold gas around the system. All right. So this is what you can take all the data. You can ask, how does the bolometric luminosity evolve with time? This is the black dots, what you see over here. The lines in the background, these are all other red novae. You can see there's this characteristic shape that they show. They show this plateau initially, and then it falls off, which is again the hydrogen recombination type 2p type light curves that we see in supernovae. And the temperatures of this event also land up in that phase space where we expect hydrogen recombination to occur around 5,000-6,000 Kelvin. So what we can show together is that this basically shows all the signs of a red nova. It gradually evolves to a very red type source dominated by infrared emission. It has this cold photosphere that looks like an M star a few months after, and it becomes dust enshrouded. We can measure the amount of dust because of the infrared emission that's coming. So why is this interesting? Is this just another, maybe produces one more galactic stellar merger that we know of. We know about 5 of these in the past. But it turns out when we started doing the numbers, there was something really striking that came about, which is that if you take our estimated distance to the source and you ask where does this source lie in this phase space plot for luminosity against timescale, you see that it's about a factor of 1,000 fainter than any other red nova phenomenon we've seen in the past. And the reason that's interesting is because the only way to explain why a red nova would be a stellar merger would be so faint. Stellar mergers are really energetic events. Why is it so faint? Is that the companion itself, the energy that produced the eruption in the first place must have been not something that is a star, but the companion must have been something that is 1,000 times less massive than a star. If you ask what is 1,000 times less massive than a star, that's about Jupiter. Jupiter is about 1,000th of the mass of the sun. So that's where we started smelling some of these signatures about what might have produced this one particular eruption. So we can ask, what does the progenitor of this source look like? This is what the progenitor looks like. This is this very faint star that is in the galactic plane. We can, what we tried to do was fit the colors and the photometry of this source to mist isochrones, trying to understand what kind of what the primary of the eruption must have been. So if you plot all of that, I won't go into the details, but what we can show is that the progenitor is basically consistent with about a 1 solar mass star that's beginning to evolve off the main sequence, just getting onto the subgiant branch. And of course, this is very difficult to do because the source is extremely faint, as you can see, especially before it underwent the outburst. So take this with 1 Jupiter mass of salt, because this is it's really based on some photometry that is relatively poorly constrained. So what do we learn if we put all of it together? So what we found was essentially what appears to be a stellar merger, something that looks exactly like a stellar merger, but which is also at the same time 1,000 times fainter than any other stellar merger we've seen in the past. And what that leads us is the interpretation that because the primary star basically looks like the sun, or maybe something that's a bit more evolved than the sun, the reason why this merger was so low luminosity in the first place is because what was engulfed in this case was not another star, which is what we see in the other stellar merger events, but a much lower mass object, which in this case we estimate was a planetary mass object between about 1 and 10 solar masses. So let's see what. Okay, so then what we did was, this is what was work done with Morgan, who is here at the CFA. So if you find me lurking around the CFA on Thursdays, that's because we've been working a fair bit on understanding these types of phenomena, trying to understand what stellar mergers do. But again, in this case, what we were able to show is that you can, because we expect stellar mergers to sort of do this kind of dance before the merger actually happens, we can take all of the infrared data, the infrared brightening that we had before the eruption, and use that to estimate the mass of the object again. And that again points to a mass ratio of the binary of about 10 to the -2, 10 to the -3 or so, which again points to an object that is about a Jupiter mass, a few Jupiter masses. So what are we looking at? So in case all of that was too much for you, this is essentially what it boils down to. This is a very nice animation created by folks at IPAC. So what we're seeing here essentially is that in the final moments, as this planet starts to graze the surface of the star is evolving of the main sequence, it's spewing out this dust. And this dust is what causes the infrared glow, brightening that happens in the initial phase. And as that happens, the planet orbit is also decaying into the star. And eventually it plunges into the star to produce this brightening of the star that we see in the optical data. So this is essentially what causes the optical outburst. All the dust around it is what causes the infrared brightening that leads up to the outburst. And of course, the dust is of course floating away, keeps floating away, and then we see the afterglow of the dust for many, many months and years after the outburst has actually happened. So why is this interesting? So planetary engulfment has been discussed in astronomy for many, many decades. And we know that this must happen in the universe because in some cases, we definitely know of these things that are hot Jupiters. So if you go back to this animation again, oops, sorry. Yes. So this planet is very close in to its host star. We think it's what would be classified in the exoplanet community as an ultra hot Jupiter. Sorry, I know nothing about exoplanets, but this is it's so close in that it would be hot Jupiter and probably an ultra hot Jupiter, which is at an orbit of less than a day for sure, as its being engulfed. And we see in hot Jupiters like this around other stars, we've actually measured periods and period derivatives for these things. So for many of these sources, you can show that by timing these orbits, that these are the orbits of the hot Jupiters are decaying. That's expected theoretically as well. So at some point, we expect hot Jupiters to eventually get engulfed by their host stars. So this has been around for quite some time. And we also see indirect evidence for a lot of this, because some stars appear to show chemical signatures of planetary engulfment, in that they show these weird lithium enhancements that have been long proposed to come from planets being engulfed by stars in the past. So what can we say about rates? So of course, doing rates with one event is very, very difficult. And I'm not even going to try to defend this, but let's say some journal asked us to do it. So you can take this one event, you can simulate what the ZTF survey does, and essentially simulate a light curve that looks like this, which is the one particular source that we looked at, and ask how many events must there be going on in the Milky Way to explain this one discovery that we found in about 2 years of data. And the number turns out to be, take that, 3 + 4 - 2 per year. So maybe one every year or so. But again, like doing rates with one event is very difficult. So what's next for this source? So now that obviously we know how to identify, we've seen one event, we can obviously go and try to look for more. But I think even for this one particular event, the story is not done yet, because if you look at our understanding of how we think planet mergers proceed, this is what a long-standing prescription has been, that the planet gets disrupted and it kind of leaves behind this disk of material around the star that hangs around for some time until it dissipates. And we can actually now go and look for these signatures, if at all they exist, around an event like this, where we think a merger has actually happened. And so we got some time on JWST. This is through a GTO program by Mike Ressler. This analysis is being led by my colleague, Ryan Lau. And what we have now is a JWST near to mid-infrared spectrum of the remnant itself. This is what it looks like. So essentially what you see is that the source still remains bright in the near infrared. Like I said, it's bright in the infrared, and it gets even brighter at longer wavelengths. But what we're able to show now is that you can actually see, I think it's around 4 microns or so, we see evidence of this disk. We see emission in the CO band heads around 4 microns that tells us that there is a disk around the star. We can see it. We can measure how far it is from the source, and then measure its temperature as well. So, so just to summarize, this event was really exciting to discover. We really started to look for stellar mergers, and sort of stumbled into this cousin of a stellar merger, which is perhaps a prediction that was long awaited to be confirmed. The rates are about 1 per year. This really provides a missing link that we've been waiting to discover. The dynamics, which I didn't go into a bit, but this is what Morgan and I are really excited about, that the dynamics of how this star reacts to the planetary engulfment is kind of curious. We don't quite understand it, but we have some clues. And especially like with upcoming surveys like LSST, where you can measure multiple colors at the same time, that's going to be a really powerful way to distinguish these events from this other zoo of galactic plane transients that we have to deal with, because these have very characteristic redward evolution of their colors with time. And of course, what the angle that I'm really excited about is that we can find these things in the infrared now. We have, I've been working with a couple of teams doing these wide field infrared cameras that are coming on. They're already online. We'll be searching for transients very soon. And because of the long-lived infrared emission, they'll be quite easy to identify when you have infrared data. So anyway, so that's it. So I'll take any questions. Thank you. Also, I guess I'm around here on Thursday, so in case can't find me this week, I'm here every week. Thank you.
Thank you so much. Very interesting. So questions?
Thank you very much.
Right. So, and the question was if you can detect changes in the brightness of the star from Gaia of the before the eruption actually happened. So yeah, so unfortunately, this source is sufficiently far away and sufficiently close to the disk that the source is actually very faint in the optical. So the only place where we see it is in the infrared. The archival image we have, the detection we have is from the Euclid Galactic Plane Survey, because it's like probably 23rd, 24th magnitude in the optical, but it's more like 17th magnitude in the infrared. So it's detectable in the infrared.
Great, thanks. You said that over time, the spectrum looks more and more like that of a M word.
M star, yes,
M
yes,
star.
yes, yes,
Um,
yes.
Is that just because it's a cooling star, or is it because it's actually becoming an M star?
Yeah, it's primarily because it's cooling. So it starts off as this sort of hotter photosphere, which is more like a maybe, let's say, F-type star. And then as the engulfment happens and as the star balloons up to get rid of that energy, especially it's the outer layers that go further and further out and cool. So yes, so it looks like an M star for a bit, but eventually as this unbound gas escapes, it's going to go back to looking like an F star again. So yes, it's a temporary M star in some sense.
Any other question? Online, something? Excellent, then let's thank our speakers again.